Hey, Trig has been pretty fun so far and like not too hard, right? Well, you know what was coming. We needed to get into some harder, more abstract stuff eventually. So here's the deal. In section 13.2, we introduced the concept of angles that are bigger than 90 degrees. So you put the one side here and then you go around a certain amount, and this is a bigger than 90 degree angle. So the natural progression is, hey, how do I interpret trig identities that are bigger than that angle? Or how to identify trig identities of angles like this, because they're no longer angles that are living in triangles, and this is confusing. So that's what we're going to tackle this section. Again, how can I find the trig identities of angles that are bigger than 90 degrees that don't fit inside a right triangle anymore? So we're going to get more in depth with this, but kind of the starting questions to help you understand what's going on here is this. We're going to find 6 trig ratios, all 6, of an angle whose terminal side is through this point. So remember, when we're graphing angles, a way that we can graph them is to put them on a coordinate plane. We always put the starting side on the positive x-axis, and then we go around a certain amount, right? So this is saying, hey, go around and put the other side so that it's through this point. So where is this point? Well, I'm over -4, up 3. So maybe somewhere like this. This is where our angle is going through. So in other words, we're looking at this angle. Here's our theta. And I want to be able to figure out what is sine of theta, what is cos of theta, and so on. But this is weird because this is not a right triangle, is it? We know that sine is opposite over hypotenuse, but only if it's a right triangle. How am I supposed to do it with this weird abstract angle that's outside of a right triangle? So here's what mathematicians came up with. They decided to do this. This is how we interpret it. They said, hey, let's put what we call a reference triangle, and let me just change my color here. We're going to put a reference triangle whose angle is like an angle of elevation or angle of depression and is a right triangle. So let me draw it for you and you'll see what I mean. Here is our reference triangle, okay? Now this is a little weird, but notice what I've done. Here's a right angle. Do I know how long these sides are? Yes. I went over -4 and I went up 3, and if I use the Pythagorean theorem, so 3 squared plus -4 squared equals c squared, I can find out that this other hypotenuse side happens to be 5. So this is a right triangle. The only difference is that this side we kind of consider to be negative, which is weird, but that's the way we're going to talk about it. The angle I'm orienting to is this angle in here. I'll call it alpha, and we call alpha the reference angle. Now, notice 2 things about the reference angle. Thing number 1 is that it is touching the origin. This is very important. Thing number 2 is that it's like an angle of elevation or depression in that it's coming off the horizontal, just like the angle of elevation or angle of depression. They come off the horizontal. So what mathematicians say is, in order to find sine of theta, it's going to be the same as looking at this triangle with alpha. So opposite over hypotenuse, 3 over 5. Now here's where it gets a little goofy. Adjacent over hypotenuse, -4 over 5. Because since I'm going left 4, I kind of consider that side to be negative. Weird, but it works. Tangent, opposite over adjacent. And again, the negative shows up here. And then let's just quickly do the reciprocal. Cosecant is reciprocal of sine. Secant is reciprocal of cosine. And cotangent is the reciprocal of tangent. So is this really weird? Yes, it's extremely weird, and it takes a lot of practice, and it might take you a while to click. So let's do another example. Let me switch back to red as you digest this example. We'll do another one. If you didn't get this one, see if you can get this one. Okay, so very similar. Find the 6 trig ratios of an angle whose terminal side is through -5, -12. Okay, so let me draw my triangle a little bigger this time. I always put my starting angle here. -5, -12 is right about here. So the other side of my angle is going down here, and here is my theta. So again, I have an angle that is bigger than a right triangle, and the only way I can make sense of this is if I use a reference angle. Now remember our rules for reference angles, or reference triangles. They always need to touch the origin. This angle needs to touch the origin, and they always need to come off of a horizontal line. You can also think about it like the way we kind of approach that point. In other words, I'm going over -5 and down -12. Notice that this reference angle is touching the origin and is coming off of a horizontal line rather than a vertical line. In other words, don't put the reference angle here. No, it doesn't make sense to put the reference angle there. Draw it off of the horizontal line, not the vertical line. Now again, we can use the Pythagorean theorem to figure out the hypotenuse. I happen to know that the hypotenuse here is 13. This is what's called a Pythagorean triple, 5, 12, 13. Notice that in both cases, the hypotenuse has been positive. Positive here, positive here. The hypotenuse, here's another principle, is always positive. Now remember, in order to find sine of theta, I'm going to look at my reference triangle, and actually I'm going to find the sine of alpha. Mathematicians consider that to be the sine of theta. And we'll talk about reasons for that later on in the second half of this section. So sine of theta is the opposite over the hypotenuse, so -12 over 13. Cosine of theta is adjacent over hypotenuse, so -5 over 13. Notice I'm using the negatives. Finally, tan of theta is going to be opposite over adjacent, and the negatives cancel here, right? I have a negative on the top and the bottom. Those cancel. Okay, let's quickly do the reciprocals. Cosecant theta, just get used to doing them in this order. Then secant theta, because remember, if you do them in this order, it will help you remember what they're reciprocals of. And then cotan theta, 5 over 12. Okay, so again, a super weird problem. Let's do one more quick example, but I'm going to try to keep this video short because it'd actually be better if you go back and rewatch it. This is super weird. Okay, we haven't looked at a reference triangle in quadrant 4. So let's say I have some angle that's starting here, and the finishing side is somewhere in quadrant 4, like this, so that theta is all the way around. The question is, what reference triangle would I use? In other words, that little blue triangle that I've been using to find my sine, cosine, tangent, how would I draw that? Would I draw it like this? Would I draw it like this? Would I draw it, I don't know any other way of drawing it. Remember our key. The reference angle needs to touch the origin. So my reference angle is either going to be here, or my reference angle could be here. But the question is, which one comes off the horizontal line? Because just like angles of elevation and depression, they need to come off the horizontal line. This is the one. This other triangle doesn't touch the horizontal line. It touches the vertical line. You need to be coming off of a horizontal line, just like angles of elevation. So you would draw that triangle to find sine, cosine, and tangent. Okay, so I know this section was really weird. Let's just summarize. Quick note. When you're finding the hypotenuse, notice that it's always positive. That's something that we noticed in example 1 and 2. Always make your triangle coming off the horizontal with reference angle touching the origin. And guys, I know this is a confusing section. Maybe go back and rewatch. We will practice a bunch. Thanks for watching.